So equipotential surface through a point normal to the electric field. So first bit answer, electric fields are normal to the equipotential surface. So these are equipotential surface. Electric fields are normal to the equipotential surface. Electric fields are normal to the equipotential surface. So electric fields are normal to the equipotential surface because work done required to move the charge over the equipotential surface is 0. Work done required to move the charge over the equipotential surface becomes 0. Work done required to move the charge over the equipotential surface is 0. So this is point A, this is point B. Work done required to move the charge over the equipotential surface. Work done required to move the charge over the equipotential surface. This is Vb minus Va into Q. So this is Vb minus Va into Q. This is V minus V into Q. So work done equals to 0. So work done required to move the charge over the equipotential surface is 0. Second bit says that when dielectric is placed in external electric field, the electric field inside the dielectric is less than the outside. So let's make an external electric field. So this is the external electric field. This is the external electric field. As this is the external electric field, this is the external electric field. Dielectric is placed within it. This is the external electric field and dielectric is placed within it. So electric field E0 is the external electric field. Dielectric is placed within it. This is positive. Electric fields are directed from positive to negative. So as this is the dielectric, at the positive side negative charge is there. At the negative side positive charge is there. Positive side, as the positive side negative charge is there, at the negative side positive charge is there. So within dielectric E equals to E0 minus EP. E equals to E0 minus EP. Resultant electric field equals to how much? Resultant electric field equals to E0 minus EP. So here electric field gets reduced within the dielectric. As electric field gets reduced within the dielectric, so as E equals to E0 minus EP, as E equals to E0 minus EP, so electric field resultant field gets reduced. Resultant field gets reduced. Resultant field gets reduced within dielectric. resultant field gets reduced within dielectric. That is the second bit. So moving to the third bit. So third bit says that the potential difference between the plates of the charged parallel capacitor decreases when its plates are brought closer. Potential difference between the plates of a parallel plate capacitor decreases when its plates are brought closer. Moving to the second page. So if separation reduces, potential difference also reduces. That is the bit C. Bit C says कि suppose this is the parallel plate capacitor in the initial case. This is the parallel plate capacitor in the initial case. Separation is D. Now the separation between the plate gets reduced. Now separation between the plates gets reduced. As separation gets reduced, electric field also gets reduced. E equals to V by D. V equals to E into D dash. So E equals to V by D, V equals to E into D dash. As separation reduces, electric field also, potential difference also gets reduced. Potential difference also gets reduced. As separation reduces, potential difference also reduces. Obtain an expression for work done to dissociate the system of three charges q minus 2q and q minus 4q 2q placed at the vertices of A, B, C, equilateral triangle of side A. So find the work done for this purpose. Q minus 4q 2q, q minus 4q 2q. So what is the work done for the purpose? Work done to dissociate the system of charges placed at the vertices of equilateral triangle. Second bit. So q minus 4q 2q. So sides are A. So this is also A. This is also A. So q minus 4q 2q. So sides are A. This is equilateral triangle. So how much work done is required to dissociate the charges? Work done required. Work done required equals to how much? Work done equals to how much? Work done equals to k naught q into 2q divided by A plus k naught 2q minus 4q by A plus k naught q minus 4q divided by A. That is the work done to dissociate the system of charges q 2q minus q 4q placed at the vertices of equilateral triangle with side A. That is the work done for the purpose. And after solving, the unit is joule. Work done unit is joule. The electron drift speed is estimated to be only few millimeter per second for current in the range of few ampere. How then current established almost the instant circuit is closed? We know that formula I equals to how much? I equals to AVD NE. I equals to AVD NE. I equals to AVD NE. This expression is current in terms of drift speed. This is the current value. with respect to drift speed. In the second case, a low voltage supply from which one needs high current must have very low internal resistance. I equals to V divided by R. Low voltage supply from which one needs high current. So if one needs high current, internal resistance reduces. If one needs high current, internal resistance reduces. Internal resistance reduces. The assertion that V equals to IR statement Ohm's law is not true. So this is V, this is I. This is V, this is I. For practical conductor, this is the graph. For practical conductor, this is the graph. Also for this is the Ohm's law. This is the Ohm's law graph, V proportional to I. In case of practical conductor, this gets reduced. In case of practical conductor, this gets reduced. Practically it's not possible, so that's why in case of practically this gets changed. So these are the points limitation of Ohm's law. According to Ohm's law, V proportional to I, but in practical cases there is a lag behind it, so that's why it is not true.